My name is Bryan Stockton. I'm the project manager of the Ultrasonic 3D printing team. My team members here with me today are Neil Desmond, Chris Savage, and Tyler Miller. Our faculty supervisors were Shandor Miturgis, who's a faculty member or a member of the physics department, and Professor Packens. So this research project is based around taking existing technology of ultrasonic welding and turning it into a rapid prototype machine. So the basis of that is vibrating an ultrasonic welding head and being able to move it along a platform that we can create whatever image we want to. As ECE students, our goals were to actually make the driving electronics to actuate the transducer, to build a sensing circuit so that we can sense the vibrations of the sensor, and then to do the motor controls in the motor to move it along the table. So the requirements for that is the ultrasonic transducer, which is essentially the printer head, has a maximum of output voltage or input voltage of 230 volts that it can take, and that's at a 40 kilohertz sine wave that we input. So the maximum amount of wattage you can take is 1,000 watts. The sensor circuit needs to be able to detect up as little as 5 microns of displacement, and then we need to display that so that we can do an adjustment to know what frequency we're getting on the actual welding tip. Motor controls, we're moving along the x-axis, and then we need to make sure it stays on the substrate so that we don't go off the substrate while we're printing, so there are limit switches that are involved with that. Okay, so I'll turn it over to Neil, who's going to explain the high voltage power supply.
Power for the ultrasonic transducer is provided by wall outlet 120 volts AC. It's converted to DC. 40 kilohertz signal, square wave signal from the function generator is used to control an IGBT. An IGBT, which stands for insulated gate bipolar transistor, is a collector gate emitter device, and it is capable of handling high voltage and current, and is less expensive than a power MOSFET. Here's a schematic showing the circuit of the power supply, and highlighted in yellow. And this is the transducer right here, an isolation transformer was used for safety purposes. To handle the current, we use large enough wire gauge, components in general with larger than necessary ratings were used. Heat sink was used on the IGBT, and the resistors were built to be able to handle enough current, enough wattage. On top of that, a cooling fan was used to keep the temperature low. A function generator was used. The reason we use the function generator is to be able to control the offset to drive the IGBT. The oscilloscope display right here is the voltage across the transducer. It's the AC. It's not showing the DC offset. Here it's showing the DC offset. When we do a PSPICE simulation of the circuit, it does a fairly good job of replicating. But when we try to replace the R3, it doesn't, with a 20 kilo ohm resistor. I'm sorry, I forgot to explain that the circuit is being powered, it's an RLC parallel circuit right here. And now Chris Savage will discuss the feedback sensor system.
Thank you. So what we were trying to aim for with the sensor section is to get a physical feel of what the actual vibrations were that we were getting from the sonotrode, which is the vibrating surface. And so we created circuitry which would amplify that signal, turn it into DC, and then initiate a counting function so we could know what the frequency was. All this was processed by the microcontroller so we could get a visual representation on screen. So our basic components that we had is we had an amplifier. The amplifier had to be a special instrumentation amplifier because it had to handle very high gains at up to 100 kilohertz with gain of 1,000. Then we simply used a comparator which acted as a 1-bit analog to digital converter. And that fed digital pulses into a a counter which just simply counted. The MSP430 is the microcontroller we used, and that took the information from the circuit for processing. We had to do a lot of testing with the sensor circuit because when we designed it, we didn't actually know what type of vibrations we were going to get out of the sonotrode until we started driving it. So we had to anticipate for a wide range of signals, wide range of noise that we would get, and such things. So things that we discovered along the way is things like bandwidth product are extremely important. Don't use 741s in systems like this. So bandwidth product. And then something that we did a lot of testing was with the actual sensor. What we did is we had to put the sensor on the scale, as you can see in this picture, and we actually varied the distance between the sensor and the sonotrode, you can see there, by thousandths of an inch, which are, you can say, 50 micrometers at a time. To find that sweet spot, so we know where the linear portion of the curve would be, so we could determine frequency and amplitude and such things more accurately. Here's a circuit design of what we did. You see the sensor, which feeds into an amplifier, digitizes the signal, and begins the counting. For the signal processing, what we did is when the 14th bit on the counter that we use goes high, it triggers an interrupt in the code. This interrupt stops a timer that we have running, and the frequency is determined simply by taking 2 to the 14th, the value of the 2 to the 14th bit, and dividing it by the timer value that we got. Then the output is displayed in an LCD, which was mounted on the outside of the box. Now I'm going to pass it on to Tyler Miller, who's going to talk about the motor control system.
Now the purpose of the motor control system is to be able to move the welding table across the x-axis at a consistent speed. So we'd be able to weld the substrate on multiple layers at a time, like one layer at a time, and repeat the same movement multiple times in order to try to develop a 3D-dimensional object. Now there's 4 main components of the motor control system. There's stepper motors, the driver board, the desktop computer, and then limit switches. For the stepper motors, we chose stepper motor for robotics. It has 260 ounces of torque per inch, which is plenty for us to drive the drive screw for the welding table. It also has a resolution of 1.8 degrees, which means it takes 200 steps to move one full revolution. Now for the driver board, we mated it with the same driver board that's recommended by robotics. It has a max output of 2.5 volts, amps, which gives it its torque of 260 ounces. It also offers microstepping. What microstepping is, instead of having one full step, you can do 8 small steps, 4 small steps, or 2 small steps. So now your resolution increases from 200 steps per revolution to 1,600 steps per revolution. And this gets its input from the DP25 pin port and parallel port on the desktop computer. Now for the limit switches. The limit switches, they're very important to use to maintain the max and min of the x-axis, so that we can always tell where we are on the x-axis. And if the motor stalls because you're overdriving it, then you just back up to the limit switch, and you know you're at the min, and then you can go 3 inches from the min or 4 inches from the min. These use metal sensing MOSFETs that detect the table coming within 0.8 millimeters of the sensor. And when it does, it triggers an LED indicator and sends a high signal back to the DC.